Hello everyone. In this video we will be discussing about solutions to a system of linear equations and also 4 subspaces in linear algebra. So a system of linear equations can be represented as shown in the slide. So Ax is equal to b, where A is a matrix of dimension m cross n, x is a vector which is of dimension n cross 1, and b is a vector which is of dimension m cross 1. So this is a very generic expression. So before we analyze the solutions to the system of linear equations, we need to see how the matrix looks like for different cases. So let us analyze for the first case where m is equal to n. So when m is equal to n, it is a square matrix and x also has the dimension m cross 1, and also the transformed vector b will also be of dimension m cross 1. So if m is less than n, then your matrix looks something like this, which is a fat matrix. So where n is greater than m, which means number of columns are more than number of rows, which also means number of equations are less than number of variables. So when such is a case, you will have a solution vector which is as equivalent to the number of columns of A, and you have the transformed vector B which would be as equivalent to the dimension, the number of rows of A. So such a system of equations is called as underdetermined system of linear equations. And when m is greater than n, you will have a matrix A which would be called as tall matrix, where m is number of rows are more than number of columns, and which also means that number of equations are more than number of variables. So your x, which is a solution vector, would be n cross 1, which would be equal to the number of columns, and the transformed vector b would be of dimension m cross 1. So it is important to know all these three cases and how the solutions, what type of solutions does these three cases have. So it is important to know these three scenarios. So let us start with the first scenario where m is equal to n, which means A is a square matrix, and x is also of dimension m cross 1 and b is also of dimension m cross 1. So basically there are three types of solutions. So first solution is a unique solution that arises when A has rank m. Rank indicates the number of independent vectors in matrix. So each column in A is of m dimension, and it spans the whole m dimension space if the rank is m. If it has m independent vector, it is going to span the whole m dimensional space. So when you have m independent vectors, you are going to have the unique solution. And when rank is less than m, which means that number of independent vectors in A is less than m, then the number of solutions depends upon whether B lies in the span of A or B doesn't lie in the span of A. So the span comes into picture because A does not have m independent vectors. It has less than m independent vectors. So the transformed vector may be in the span of A or may not be in the span of A. If it is in the span of A, then you will have infinite solutions. And if it is not in the span of A, then the number of solutions would be 0, which means that A has less than m independent vectors and B is a vector which is coming from the vectors, the independent vectors which are not spanned by A. So let us take an example and understand how such a scenario looks like. Let us take this example where A is a 2 cross 2 matrix which contains 2 independent vectors. So rank is 2. So it has a unique solution because A spans whole 2-dimensional space, and whatever may be the B, it will always be in the span of A. So it will always have a solution, and that solution is always unique. So let us take a different case where A has rank of 1, which means that it has only one independent vectors. As you can see here, the column vector 1 1 and the column vector 2 2 are dependent. If you multiply 1 1 with 2, scalar 2, you will get the second column. So when such is the case, you have to check whether B is in the span of A or whether it is not in the span of A. Let us take an example when B is equal to 3 and 3, which means that B is in the span of A. So span, we can find out whether it is in the span of A by linearly combining these column vectors of A and check whether it is forming or whether you are able to get B. So for some scalars, if you are able to get B as a combination of A, then B is in the span of A. So if B is in the span of A, then you have infinite solutions. If B is not in the span of A, then you have no solution. So which means the A is not covering the two-dimensional space. It only, since its rank is 1, it only spans in the one-dimensional space, and the vector B is coming from the other dimension, and that is why A is unable to transform X into a vector B. Okay, so you will not be having a solution you will not be having an X which will transform A into B. Let us take the second case, which is m less than n, which is called as an underdetermined system of equations, where A is a fat matrix and X is a n cross 1, which is a very tall vector, and B is of m cross 1. So there are two types of solutions for a underdetermined system of equations. You will either have a infinite solutions that arises when rank of A is m, or when rank of A is less than m, but B is in the span of A. In any of these two scenarios, you will have infinite solutions, but you will have no solution when rank of A is less than m and B is not in the span of A. So if B is not in the span of A, you will definitely have no solution irrespective of any case. But if rank of A is spanning the whole m dimensional space, then B would definitely be in the span of A. So that is one important thing to remember. So in underdetermined system of equations, we have two categories of solutions, infinite and no solutions. Let us see with an example how it looks like. So let us take a matrix A as shown here. So it's a 2 cross 3 matrix and it contains two independent vectors. So rank of matrix is 2. So since rank of matrix is equal to the number of rows, which is m, which is equal to 2 in this particular case, so you will have infinite solutions, which means that for any B, it has sufficient number of independent vectors to span, and also it has also dependent vectors, which makes it to have multiple solutions. So it has an infinite number of solutions for this case, and so this is one case. So what happens if rank of matrix A is less than m, which is the number of rows? So if rank is 1 in this particular case, as you can see, we have to check whether B is in the span of A or not in the span of A. If B is in the span of A, then let us consider this example where B is equal to 7 and 7, which is directly a scalar multiplication of any of these vectors given in matrix A. So when such is the case, you will have infinite solutions, and when B is not in the span of A, we know that it gives no solution. B is not in the span of A because A is not spanning the whole m dimensional space, and there will always be a vector B which can come from the dimension which A is not spanning. So when such is the case, you will have no solutions. So these are the cases in underdetermined system. Let us also see overdetermined system of equations. Overdetermined system of equations arises when m is greater than n, which means when number of rows are greater than n. number of rows are greater than number of columns, and number of equations are greater than number of variables. So when such is the case, your solution vector would be of n cross 1. So solution vectors are always of dimension of number of columns. So and the transformed vector will always be of dimension number of rows. So what would be the solutions when for an overdetermined system of equations? So there are three types of solutions. So when rank of A is equal to n, so it has to be noted here that rank of A can be it is always less than the minimum of m comma n. If it is a tall matrix, it would be less than n. If it is a fat matrix, it would be less than m. So if rank of A is equal to n, which means it's a full column matrix. So when such is the case, and if B is in the span of A, so if it is in the span of A, you will be having unique solutions. And if B is not in the span of A, so you will be having no solutions. And there are other cases when rank of A is less than n. Rank of A is less than n, and if B is in the span of A, you will have infinite solutions, and if B is not in the span of A, it has no solutions. So in summary, like when B is not in the span of A, irrespective of the situation, it will not have the solution. But why there is a unique solution when B is in the span of A for overdetermined system is you have it has enough number of vectors, independent vectors, and when for the infinite solution case, you have dependent vectors, which makes it to have infinite number of solutions, whereas in the unique solution case, you don't have any dependent vectors which make it to have more than one solution. So if rank of A is equal to n, you will not have any dependent vectors, and therefore you are having unique solution. So this is for the overdetermined system of equations. If we see with an example, let us take this example A, which is of dimension 3 cross 2, which has rank 2, and you have to also remember that rank of row space and column space, which are the terminologies which I am going to introduce in the next slide, will always be same. So if rank of a matrix is 2, its row space and column space will also have a dimension 2. So dimension we use the terminology when we talk about spaces. For a matrix we call it as rank, but more or less they are same. But dimension should not be confused with the order of the matrix. So sometimes the order of the matrix is also called as the dimension, so not to be confused with that. So if you have such a matrix A, so there are two cases. So if B is in the span of A, which means that B is some linear combination of A, then you will have a unique solution, and if B is not in the span of A, then you will have a no solution. This is for the case where rank is, it has a full column rank, which means that it cannot have more than that particular rank. I have said that rank is always less than m comma n, minimum of m comma n, and here minimum of m comma n is n, and so here in this particular case your n is equal to 2 and it cannot go more than 2. So the A has achieved its maximum rank, and therefore it has unique solution. There are no dependent vectors, whereas when A is having a dependent vector, so which means that there is rank is less than 2. In this particular case rank is equal to 1. So when such is the case, once again you have two cases. When B is in the span of A, which means it comes with some scalar multiplication of the columns of A, so then you will have infinite solution. You are having infinite solution because there are dependent vectors, because rank is equal to 1 indicates that there is only one independent vector and the rest are all dependent vectors. And if B is not in the span of A, then you will have no solutions. So which means that none of the combinations of the columns of A can span the vector B. B is coming from a dimension which is completely outside from the dimension of the vectors which are spanned by A. So in summary, we have following cases. So first, it has to be noted that there are cases where we have written it as does not exist, because when rank of A, when A has achieved its full rank, then when in the for a square matrix case and for a fat matrix case, even there is nothing like B is not in the span of A. That's why we have written here it as does not exist, because B is always in the span of A when rank A achieves its full rank. So in the same way, if rank of A is, so when rank of A is less than m minimum of m comma n, there is a possibility to have infinite solutions, because if B is in the span of A, you will definitely have the infinite solutions. But if rank infinite solutions is mainly due to the existence of dependent vectors. So as if we have dependent vectors in the matrix A, we would be having infinite solutions if B is in the span of A. If B is not in the span of A, then we will be having no solutions. So irrespective of the case, as you can see here, for all the three matrices, if B is not in the span of A, we are getting no solution. Coming to the unique solution, since there are no dependent vectors and since A has sufficient number of vectors which can span the whole m-dimensional space, which is like it has m independent vectors which can span the whole m-dimensional space. Therefore, for any B, it is having the unique solution. This is happening for both the square matrix and also the tall matrix. So this is the summary of all the solutions for Ax is equal to B. Let us see now 4 subspaces, which are row space, column space, null space, and left null space. More particularly, we would be focusing on null space, as there is a correlation or there is a relation to what we were discussing earlier. So there are 3 different cases. Once again, we have a square matrix where it has k independent vectors and there are m minus k dependent vectors. If it is a fat matrix and if it has a k independent vectors, how does the solution for a null space exist? So we'll be seeing that. And for tall matrix also, we assume that there are k independent vectors, and we will see what kind of solutions it would be having. So first of all, let us define what is a null space. Null space is a subspace of Rn formed by the solutions to system of linear equations Ax is equal to 0. So till now we have seen Ax equal to B, but now what we are seeing is Ax is equal to 0. And it is an n-dimensional space because we are trying to see the solution space of X, and X is of dimension n cross 1. So one of the trivial solutions to Ax is equal to 0 is 0 vector. So 0 vector, irrespective of the matrix A, 0 vector is always a solution to Ax is equal to 0. So if rank of A is equal to k, which is less than minimum of m comma n, then following cases arises. So since matrix A has k independent vectors, which is less than the minimum of m comma n, which means that it is not a full column matrix or full row matrix, so it will not be spanning the whole m-dimensional space. So rank A will not be spanning the m-dimensional space, which means that it has dependent vectors. So when it has dependent vectors, there is possibility for infinite number of solutions, and we have already seen that 0 vector is a trivial solution, which means you only have 2 cases. One, you have a unique solution which is 0 vector, or you have infinite number of solutions. So as you can see here, so since dimension of null space is n minus k, we have seen that X is in the X is a n cross 1 matrix vector, so it spans the subspace of Rn, and since rank of matrix A is k, so the rest of the n minus k dimensions are spanned by the null space, and the usually dimensions of row space and column space are same, which is equal to the rank of the matrix k, and which also means that there are k independent vectors. So if there are k independent vectors, the rank of A is equal to k, and the column space and row space dimension is also equal to k. And it has to be noted that row space, the number of columns are n, which means that the row space is also spanning Rn. So since we know that there are k independent vectors for row space, the rest of the n minus k vectors are going to the null space. In the same way, since column space has k independent vectors, the rest m minus k will be going to the left null space. So these are the four spaces which exist in linear algebra. Row space and null space are in n dimension, column space and left null space are in m dimension, and row space and column space has same dimension, so the leftover independent vectors will either go to null space or this to the left null space. So that is about the null space and how it impacts the solutions. So in summary, we can write something like this. So here we don't have anything like B lying in the span of A or not lying in the span of A, because there is always a zero vector, and which will result in the zero vector, which will transform into a zero vector. So we have to analyze for these two cases when rank of A is less than minimum of m comma n and rank of A is equal to m comma n. If rank of A is equal to minimum of m comma n, for square matrix we already know that it has a unique solution, and that unique solution will become the trivial solution, which is a zero vector. The same thing happens for the tall matrix. So which means that tall matrix, when rank of A is equal to the minimum of m comma n, it achieves the full column rank, and therefore it has a unique solution, which is the zero vector. When rank of A is less than minimum of m comma n, that means there are dependent vectors. Whenever there is dependent vector, there is possibility of infinite number of solutions, and therefore we see for all the cases we have infinite solutions. And we also have infinite solution for the fat matrix when rank of A is equal to minimum of m comma n, because there are dependent vectors in the fat matrix. As you can recollect, fat matrix has more number of columns, which means that apart from the m columns, you also have n minus m columns, which are all dependent. That's why we have the infinite solutions. So this is a summary of whole solutions for Ax equal to b and also for Ax is equal to 0. Thank you.